We'll be starting very shortly. I was just about to start, and then 10 more people showed up. We'll let them grab some pizza. If you didn't guess, this is me. There's a lot of utility to data engineering. We're just in there. We got our special equipment. We're working. And you'll see it's very applicable when I show you my little teeny demo before we get into the other speakers. Oh, wow. I mean, they came up with the design in China, so. Now, if anyone has preferences, we're setting dates for the 2025 meetups. So if there's times of the month that are better, we make sure they're not the same time as the AI camp ones. We talk to Bill and make sure we don't, make it so you got that very hard choice there. So if you have any preference, leave it in the meetup group or on any of the LinkedIn posts. Just let us know and we'll make sure we try to pick the best dates, not just the date that's not AI camp. If there's a conference or something going on, some holiday, we'll move them. There's a lot of options, but we plan to have one every month for the entire year. We'll see if things slow down towards Christmas. I don't know. Holidays get to be a little rough here on the East Coast. West Coast, they're like, yeah, sure, you could do it. We are going to have a hackathon early next year. We're doing one a little before then in California, and we're going to replicate their success over here, which means I'm going to wait to see if it, get all the tips so we know how to do it. And then we'll do one over here. It will probably be in this facility, maybe a different one if we can work with the Flatiron School or someone else. This place is pretty good. They let us get in pretty early, so this might be a good place for hackathon. And again, maybe we'll have some of our speakers want to collaborate with us on this one. Probably won't be till April or May. Milvis is the project. This number went over 30,000. It's pretty cool one to use. And one of the reasons why people were saying, what about Redis or something else? You could store vectors in, anything. But we have a couple of features that are kind of unique in scalability that people like Alibaba and others use because we could scale to billions, which is nice. The feature I like, and that helped me for capturing ghosts, is the ability to do a hybrid search. So I can store up to 10 vectors in the same collection, which means I could use different embedding algorithms. Some are better for different types of data. Some are better for different types of search. So it gives you lots of variables on how you can find data, how you can find them quickly and combine them together. So I could search a image using text using image, combine both results, have multiple results. And for my example, I'm actually able to combine a couple. I won't show you this one first. This one's a simple one. This is just doing using a model to be able to search images with text. That's a simple one. So what we're doing is taking a bunch of different models for embedding and vectorizing the data 4 different ways so we can find it in different mechanisms. The data happens to be ghosts, but it could be anything. I wanted to bust these ghosts because I'm like, hey, what is a ghost? It is definitely unstructured. It's definitely hard to define. So I'm like, well, that doesn't go in a regular database. How am I going to do that? There's no primary key, there's no description. So I kind of got some metadata for it, which I could have probably used a catalog if I had one. I don't know, maybe someone will help me with that. So I just put some metadata so you can use different ways of gathering data on specters and unexplained apparitions you might see. If you see any at the meetup, definitely let me know. I did not place any. We don't have that kind of budget here. But we can capture with a Google form. I also have a runnable Streamlit app that'll let you enter your data. And I also do a bulk load where I just grab these from previous reports of these ghosts. What's nice is I could store these in a bunch of different ways. And if we look at the different algorithms here, I'm using a BGE M3, which is a cool new model because this lets me pick sparse or dense. I could have done dense and sparse from the same one, but I decided to use Splayed for my sparse matrix because that one's kind of cool and I like the name. I don't know if that's the best way to use something, but there's a lot of different models. If the results aren't good, try a different one. Also doing Clip. Clip is one of the new multimodal models that lets you do text and image in the same way. So I can take text, run this embedding model, and it'll map into the same vector space as an image, which means I could search for an image either way, which is fun. And I'll show you that with some of these analytics in here. So for this one, this is a simple one. I'm just doing a search based on a text here, ghost with a skull head. Sounded cool to me. So I encode that with the same model I could have done an image. I put a filter on there so I don't get all the classes of ghosts, you know. We just get some of them. I get back the ghosts that match, and I format them nicely so you could see them. I could also search via ghost. So I have a ghost here I'm going to use to search with. And I just say not fake. We don't want to deal with any of them fake ghosts because that's not cool. And then I just make sure that the distance, how close it is to my search result is close enough that I say, yeah, that's really a match. See, these are kind of similar. These happen to be AI generated ghosts. Someone's trying to pull a fast one on us. I probably should have a category for AI generated ghosts versus real ghost. I live in an 1887 Victorian. I could tell you what a real ghost looks like. I've been trying to capture them, but it's a little hard. So the unique thing here before I hand this over to our next speaker is what a hybrid search looks like. People might have mentioned this and they're like, oh, I can combine these two things. Well, I'm combining a lot of things. So here I take a text query, brown flying ghost, encode that. That is one search against one vector. This is the vector named very creatively vector. I'm really good at naming vectors. Then the second one is a text model. That's vector 2. This one I'm encoding here with the text model. And then I'm going to take that same query and code it with my sparse encoding and do that against that same vector, the text one. And then here I'm going to grab an image from my Minio server, download it, encode it, and use that to search against that same first vector that does the multimodal search. Combine all those together, add the BGM3 dense search, all those four of them, do my hybrid search, give me back a couple of fields, give me 10 results, and that's the timing. It's pretty quick. And then I iterate through all those, unless I crash something, and we get the results. Do I have to run these all again? I might have to run these all again. Oh, I got to keep running, go back until I get it all. I don't think we have time to run every part of the model here. So this iterates through it, gives us the distance, and then we'll display the images that are stored in the vector database. And then we could do other stuff, which is pretty cool in Jupyter, display stuff as Markdown. So I can build up a report on my data. And for part of the reporting, when I insert the data originally, I call a lava model that can look at an image and give me a really good description of it. I've been surprised at how good these descriptions are because this is a open model that's running on my laptop. So I'm pretty happy with that one. That one's, oh, I know why. It's pointing to my server at home. That's not going to happen. So we're going to move to the next speaker. He's going to attempt to do his talk from this laptop. Hopefully you're not haunted here. But this is a very cool one. Uri's going to be talking about intro to vector search. He's okay.
Okay, first of all, thank you all for coming. And this is going to be a pretty introductory talk to vector search and why do we actually need some fancy things like Milvus and other vector search engines, and why can we just iterate and do matrix multiplication. So hopefully by the end of this talk, you know the capabilities of vector search and vector stores. So let's get started. This is our agenda for today. A few words about me, about Argmx. Then we'll talk about recommendation systems. We're a search and recommendation consulting firm, so we care a lot about recommendation systems. Then we'll talk about approximation algorithms. And this is the main reason why you probably need a vector search, or at least you should care about vector search if you do anything at scale. Then we'll talk about similarity search architectures in general. And then we'll talk about what I think is the new standard for vector search and database. So let's get started. This is me, my two sons and dog. Actually, we now have two dogs. I organize, I'm one of the organizers of PyData NYC, also a pretty cool meetup. I have a podcast in Hebrew. If you didn't catch my accent, I'm originally from Israel. One of the, it's not that hard, but one of the most popular podcasts in Hebrew on machine learning. I used to work for Microsoft, AT&T, Yahoo. Then I founded a machine learning startup for analyzing legal documents that was acquired by a company here in New York in 2020. And then I started Argmx, a consulting firm. So this is me and my history. Argmx caters for 2.5 sectors. Our two main sectors is our edtech, advertising technologies, companies like F-Flyer, Sport Illustrated, etc. So we have quite a few insurance companies and financial services companies. And a rising star is companies developing tools for creator economy. If you might have heard about companies like Artlist, Lightrix that develop tools for content creators. Cool. So who here never heard about a recommendation system or doesn't know what it is? Who here designed the recommendation system? Cool, so only one? So two. That slide is a bit pretentious, but essentially a recommendation system is any use case where you have a lot of items. You can think about products, ads, resumes if you're looking for a job, and you have a lot of users, but you have limited space. So you need to make a decision which items are you going to show to which users, and you need to be kind of conservative about that. So most recommendation systems are essentially a ranking problem, and sometimes you can kind of play with that, like what is at the top, what's at the bottom, what is after a click. But that's like a pretty bird's eye view on recommendation systems. In theory, we can think about it like having some huge imaginary matrix of all of the possible users and all of the possible items. And if we are able to predict in advance, would John here in the yellow circle, would he buy a jar of cookies? Yes or no? That's in theory what we want to do. And we don't actually do that. We actually try to segment users and sometimes to represent items by their features and not by their IDs. And we're trying to predict what is the likelihood of John or people like John to buy cookies or any other sort of carb. That's the theory. Now that we have these probabilities that we're trying to predict, if we're able to vectorize the cookie jar into a vector, all of the items into vectors, and all of the users into vectors, such that their multiplication would be approximately that big matrix, then essentially we're in the gold. And why is that? Because we can use those same vectors for two use cases. The first is to have user-to-item recommendation. This is like the Spotify For You page or something like that. But we can also have the product page recommendation. When you, for example, when you visit the product page for cookies, you can see, I don't know, ice cream and other things, other sweets, because their vector is similar to the cookie vector. So one solution, one vector presentation can essentially cater for two use cases. Now, how do we actually do that? So unfortunately, I don't have the answers. There are a lot of courses on recommendation systems. A lot of people did a master's degree on various ways how to actually vectorize items and users. There are roughly two extremes. One of them is to do content filtering or content representation, trying to understand the content really well. For example, if John is vegan and the product is vegan, and in this representation, we can actually assign a value for each feature or each property, then we can recommend vegan items to vegan users. It could be keto or any other property that you can name. This is content filtering. The other extreme, also known as collaborative filtering, is not caring about the items at all and about the users at all, saving them, regarding all of them as IDs, and just trying to recommend similar items to similar users. For example, if a certain user buys both keto items and, I don't know, sports magazines, they doesn't have to share the same features. They just co-occur. So that's the other extreme. In reality, we kind of mix and match. So it really depends on the use case. Cool. So let's assume that we have this crazy magic encoder that encodes an item. And we can also train another encoder that would vectorize a query. We have the same architecture for just simple search, right? Now we can vectorize with a lot of models like OpenAI and other embedding models, BGE, Splade, that Tim mentioned before. But in theory, once you have this black box of an encoder, this is how a search looks like. Pretty simple. And what about personalized search? Almost the same, right? We just add the user vector, we concatenate them, and there you go. You have a personalized search architecture. It sounds pretty simple because it is. No, just kidding. There are a lot of details that needs to fall into place. But the bottom line is that we have a lot of vectors, right? And someone needs to manage them and actually make them to put to good use. Okay, so let's start with the basic question. There you go. This is an implementation, a full implementation. It's actually working over vector search. So what's the problem with this implementation? Why do we actually need Milvus and other fancy tools if this pretty naive implementation works? Any ideas? So the answer was essentially the complexity. And this is true. So let's try and think about vector search at scale. So this is kind of a back of the envelope calculation. Let's assume that we have M users and N items, and the dimensionality of the embedded vector is D. Then we have a lot of operation, M and D square. Plus, we actually need to sort the items, right? So we have an additional K log K complexity, which as N and M goes to infinity and you have a lot of items and a lot of users, is very costly. So this is why the naive approach is not always the best solution. So on the other hand, if you can do the naive approach, do that, right? If you have 1,000 items and even 1 million users, you'll be just fine. That's something that you can run on your local PC without too much effort. Now, another advantage of using the naive approach is that you can be pretty creative with the distance metric. Most of the distance metrics that you'll see in models these days are like inner product, cosine similarity. you won't see anything fancy like a Levenstein distance or anything like that, because it's hard to optimize. But if you're doing the naive approach, sure, do whatever. But as mentioned, the problem is scale. And let's talk about our first heuristic. I'm going to start with hierarchical search because this is the most commonly used heuristic. By the way, also used in Milvus. It's also known as the HNSW. I think it stands for hierarchical, nearest, small world, something. But sorry? What he said. But what's important is the H, is the hierarchy. So what's the main idea here? So let's assume that I'm searching for John, and I'm looking for John K nearest neighbors. That's our premise. Now, if I know something about John, I don't need to search the entire world, right? I can start by searching his zip code, right? Looking for, I don't know, 1,000 neighbors. And if unfortunately his zip code only has 2 neighbors, I can go one level up and look in his state. If I didn't find enough neighbors in his state, I can look in his country, and so on and so on. So assuming that I have a hierarchy, it really helps speed things up, and I don't need to look in all of my possible candidates. Why is that an approximation? Well, can this strategy actually go wrong? Great answer. So this strategy doesn't work if John is actually like on the border of 2 states, for example, right? Because then you're going to find a lot of neighbors that share his zip code, but are not actually the closest neighbors. So that's an approximation algorithm. It's the most popular one. It's pretty scalable, and it's the de facto standard in most vector searches these days. Another alternative, commonly used in sparse vectors. For example, algorithms like Splade that Tim mentioned before use variants of inverted indices. One known algorithm is the IVF. I'm not going to try to elaborate on the initials this time. And the idea is as follows. If I know that the majority of the entries of the vector are zeros, I only need to look up the non-zero indices in order to estimate the inner product. Right, so you can think about a huge vector, for example, the size of the vocabulary, 300,000 words, that has only 3 non-zero values. I can search only for other vectors that have other non-zero entries in that specific indices. It's very efficient, right? Because I don't search the entire globe like the previous example. I only search a small subset. But it's approximate. For example, if I have a vector with a lot of non-zero entries with close to 0 values that might have sum up to a huge value, then I'm going to miss out. So this approach is pretty useful in search engines like Lucene, Elasticsearch, in which we use the bag of words representation. And the last approach, which is probably the fastest one, but also the least accurate, relies on hashing. But not only hashing, this is the locality-sensitive hashing. We're trying to hash values in some manner that preserves some of their proximity. Not all of it. For example, let's take this pretty simple approach. Let's assume that this is John's vector, right? I can hash it only to keep the sign of the vector, right? Minus, plus, plus. And then look for neighbors in the same quartile. So it's not the same, right? It's not super accurate. It has some sort of distance aspect to it. It's super fast because hashing is super fast, but it's the least accurate. So this is kind of our last resort. For example, if we have a lot of hardware constraints, this is probably the best use case, but it has also the lowest recall. There are definitely other approaches, but these are the three main branches of approximate vector search. And let's try to summarize what are the trade-offs. So obviously, if you can do a flat naive search, it's the best approach. It doesn't really scale. And the most efficient one is the LSH, but it's also not as accurate as you'd like. The de facto standard for dense vectors these days is HNSW. And IVF is probably the standard for sparse vectors. So that's roughly sums it up. So now we know how a vector search is actually built, but how do we use it to build something that actually provides value? So this is how recommendation systems looks like. Let's assume that I have a user. I know how to encode it. And I already indexed all of the items in my vector search. This is a pretty simple search or recommendation flow. In most cases, we also would like to incorporate partitions. For example, if John here really likes bagels, but John is currently traveling in France and there aren't any bagels in the stores, it doesn't really help me, right? So I want to recommend the item, the most similar available item, right? So you can think about it conceptually as having several vector searches, vector stores for each partition. This is not necessarily how things are actually implemented, but conceptually, it's a good way to think about the problem. And this pre-filtering is pretty helpful when I know in advance what I'm going to filter on. Sometimes I don't. For example, what if the product is no longer available, out of stock or recall or anything that I can't really recommend it and show it to the user? This process is called a post-filtering because I cannot know beforehand what item is going to be available or not. One pretty common technique is just to, if I need 10 items, to query for 15 and hope for the best. There are some more sophisticated search engines that can kind of incorporate some of the filtering logic into the query. Vector searches like Vespa. I'm not sure if Milvus can do that. And Milvus, obviously. And this is the post-filtering part of a recommendation system. And there are quite a few vector stores. And I'm pretty sure this doesn't really cover even 50% of the available vector stores these days. We are a consulting firm. We do not have any preference, but obviously Milvus is the best, right? Now, regarding which one is the best and features and all of that, I would just let you decide for yourself. There is this pretty cool website, and I'm pretty sure that since I took this screenshot, a lot of things changed. This is annbenchmark.com. Here you can see how each open source vector store scales. There's also another website called the bigannbenchmark.com for vector stores of size billion and more, if I recall. But it really depends. If scale is what you're looking for, annbenchmarks.com is pretty helpful. There are also other considerations that you might want to think. And I try to list some of them in this very not so approachable slide. What data are we indexing? Is it dense or is it sparse? Some vector stores handle dense data better. Some are kind of hard-coded to sparse data. Do we need to update the vectors after we index them? Delete or modify? Some vectors searches support them, some do not. For example, the HNSW algorithm has some problem with modifying vectors after indexed. Do we need to support, do we use the GPU or not? Do we want to run it on an edge device or not? So a lot of considerations that you need to take into account. And I think that the most important one is are we running the queries one by one or in batch mode? So again, pretty important. Which brings us to like the most inconvenient question for team. Is vector search a product on its own or just a feature in Postgres or Redis or another database? So Tim, what do you say?
It's clearly a product because of the amount of things you need now to be in production.
Cool.
The level of features, backup, restore, security, encryption, different type of searches, different type of indexes. All those things are a lot to expect from someone who builds a completely separate data.
So you all heard Tim. It's definitely a feature. And this is how we regard vector stores. We try to be as agnostic as possible to the vector store. And there are a lot of libraries like the Vexim API. And this is a library that we developed. There's also a similar library by Redis. A pretty unknown library, LangChain, maybe you heard about them, also have an abstraction to the vector store. And I think that this is a good way to go. From our perspectives, some of our clients use Mongo, some of them use Postgres, some of them use Redis, some of them use some cloud provider offering. And if you want to be agnostic and not to be in a vendor lock-in, you probably want a level of abstraction above your vector search. And there are quite a few. Also Chroma that I didn't mention here. Cool. So it was a pretty long talk. So this is the gist. Think about vector similarity as a new standard. And like databases where you have a connection string and you're pretty agnostic to database, use some sort of an abstraction layer so you won't be, so you will be agnostic to the vector search. There's a trade-off between performance and accuracy. We've seen that across the three approximation algorithms, HNSW, LSH, the flat, and the HNSW. And think about your use case. Not all use cases require very high scalable data. Some of them are simpler to manage. That's it. I hope you had fun and learned something.
Very good talk. We have Lisa coming up next with the best costume of the day. I'm kind of mad. I should have dressed like the Borg, but what you gonna do? Next time.
Do we have any actual Star Trek fans in the house?
Oh, yeah.
Okay, I see you. We're gonna have some trivia at the end, so make sure you have your phones ready to Google it so that I don't know that you don't actually know the answer. Okay, I'm good to get started, I guess. Okay, thanks everybody for coming. I'm coming in from San Francisco. I was just at the Chill Data Summit, so if there's any data engineers in the room, please raise your hand. Okay, we're gonna educate some of the folks around us on some data engineering, but also some data ops. So my talk is around metadata lakes. If you have heard of the term data catalogs, you're going to get much more in depth with that concept today. Yeah. Okay, and I'm guessing this works. Cool. So I'll be working my way around both sides. I'll try my best, but I feel like this side has missed a little bit of love. This QR code goes to my LinkedIn. This is because when you just search Lisa Cow on LinkedIn, I don't exist without that N. So if you want an easier way to find me, please use that QR code. I'm the product manager and a DevRel person at a company called Datastrato. And so essentially, we're the creators of an Apache incubating project called Apache Gravitino. And that's sort of my relevance to this entire situation. I also do some work with the Linux Foundation, mostly with OPIA as a developer experience working group lead, LFAI in data, etc. So basically, a lot of my community work and a lot of what my career has been up to this point has been really trying to find this intersection and common language between DevOps data engineering and machine learning engineers, because these three worlds are completely siloed from one another, and it is causing things to break in production like you would not believe. So we're going to try and talk to each other a little bit more, and that's kind of why I'm here. The reason why I mentioned this all and kind of my issue is that POC RAG, and thank you so much for the introduction to vector search, by the way. I don't have to recall any of that, so thank you. Is that a lot of the RAG that we see is sort of like on a Jupyter notebook in a laptop somewhere, and it's very POC. The huge issue with this particular graph, it's very informative, but it assumes that all of your data is just stored in one place and it's just ready to go out the box. How unrealistic is that? It's pretty unrealistic, right? There's no crying step here. There's no crying to your data engineers to go, oh my God, why is this data in such crap format? Why is it broken? Where are all these null values going? And so that's actually arguably a huge part of the puzzle if we want to actually create enterprise level data and machine learning systems. So it also assumes that maybe this is perfectly version controlled, that it's been cleaned, it's been prepared, that there's a standardized format there. All of these things are somebody's job, right? It's not just something that we get out of the gate. The reason why this is also difficult is because there's a level of knowledge management here that's really hard to get right. When we're building a RAG system and we want to consider it a product that we can share to other people in the organization or even to other organizations, it's really hard for us to understand what the document's velocity is, how many documents we're working with, what's the lineage, maybe how these different documents have been transformed, and the actual lifecycle management. A lot of this lives in the metadata, but it also resides in a lot of different tools. And obviously, no one tool is really perfectly end-to-end, and so we miss a lot of that. And so in my opinion, just as we're starting to think of data products in data engineering, we should also think of RAG products, right? How do we conceptualize the way that we share these different pieces so that they're reusable to the organization? This is especially important because the way that we actually do RAG these days has changed quite a bit to become more complex, especially as we try and increase the performance of our generative AI applications. Fine-tuning is a lot different than actually having multiple agents and governed agents at that. And so really, there's a lot of different steps here. And the more complex we get in terms of our R&D and our innovation, the harder it is to step back and really put in the guardrails in place for us to have good, clean hygiene in our systems. So there are a lot of challenges, of course, when developing RAG, and a lot of these also stem into the data engineering context as well. Of course, the more complex your queries are and the more challenging you're wanting your questions to be, you're going to have a lot of lag there. It's going to be heavier in terms of load, and there's a lot of nuances that are maybe going to slow down your actual results. You have to synthesize information across different modalities now, so not just text, but also relational stores, unstructured data, maybe even video, and you're having to do this, and of course, application or streaming data. And so you want to have this like real-time synthesis, right? Especially if you want to do some sort of real-time generative AI. There's, of course, the data privacy and security piece of this, where really, we need to have our masking in place. We need to have our tagging in place. We might want to encrypt pieces of data. It is extremely hard once you get an answer out of, say, a chatbot to then trace back if it was then pulled from data it wasn't supposed to, right? This is kind of more of a preventative measure than a proactive one. And so it's really important. There we go. Yeah, it's really important to get this right. And of course, these systems and applications are living, they're organisms. They grow and they mutate over time and they take different shapes than what we initially intended them to. And with that, the context actually changes. The data that we feed into it changes. The information is completely different. And we need to be able to measure these things and anticipate them over time. Cool. Let's see. Okay. My good. We might just have the entire talk here at this slide. Maybe this doesn't work. Okay. Yeah, I might have to do this. No, it seems to be working now. Okay, so we talked about the complexities in terms of developing RAG applications. I want to talk a little bit more about the data now. So essentially, as cloud native data has kind of become more prevalent and we have all these amazing cloud ecosystems that have popped up, we've also become locked into the different tools within these ecosystems, whether or not it's AWS or GCP or Azure, or you're still doing a lot of on-prem stuff. Generally, your data is going to not just live in one place, but multiple places at the same time and across multiple formats in different stores. Not only that, but it might also be geo-distributed and you might have different requirements in terms of keeping that data in different locations. This can be really tricky when you're trying to create something that essentially utilizes all of your data at once to create something that's more performant. Generally, this can be really hard, right? Especially if you've got vendor lock-in going on. Of course, alongside all of these different geo distributions, we have the actual nature of data lake architecture changing. So a lot of folks might know that we started out with a single data warehouse, and then as things got more complicated, we moved to different formats and different architectures that might have suited our needs. So I'm going to go over this a little bit. A data lake is where you're just dumping all of your structured and unstructured data kind of in the same place, and then praying to God that it's just going to magically not get messy. That totally didn't work. And a lot of organizations are being punished for that now, for not having that proper hygiene. And so we've moved towards more of a lake house format where we have some semblance of structure, but still retaining this giant pool, but having more governance and metadata management in place here. And of course, there's data mesh. Data mesh is not necessarily widely adopted at this moment, but generally speaking, it's this idea of we create data as products and we have the domain owners as like business units own their own data and then serve them in this decentralized way. And of course, I'm going to point out here that in the lakehouse and the mesh layers, you're going to see that metadata and governance play a really large part in this. And this is because metadata powers data management and who accesses what data, what quality the data is, the freshness of the data, and different things like that. This is the 24 landscape. This is out of date, and I want to point out too that this is cropped. If you can find Milvis in here, Tim might give you $10. Sorry, Tim. But generally speaking, we've talked about the complexity in terms of storing your data in different places across different cloud systems. It's now also being stored in different architectures and across different tools, right? This is an ever-growing space. And each one of these tools has a different place in different pieces of organizations that you might have. And it's really important for us to recognize this because it adds to the complexity of everything, right? That single circle that I had earlier really stems from, like, it's masking this larger issue of we have a ton of work to do to even get the data in a place where then we can build a RAG application on top of it. So the first that I want to point out is that there is an operational silo that occurs when you're operating in different teams, in different departments, in different countries. This is going to have different inconsistencies across your organization, and it's going to provide a lot of headaches for you, especially if you're trying to find some sort of semblance of harmony between your operational and your analytics data. Of course, there's architectural complexity, so the way that your organization is actually structured. Different teams might not talk to each other. They might not share the different pieces of data that they actually have. And of course, if your company has done things like acquisitions, you might also not necessarily have the physical means to move data between themselves. And of course, there's the tooling silo, and largely in part because machine learning engineering teams are so focused right now on innovation and R&D, a lot of these tools we don't necessarily keep in mind with the production readiness and deployment and long-term maintainability of them. And so, how do we actually maintain and monitor these different applications once they're living their full lives? We have kind of limited tools around that. So it's really important to consider too that data governance. Maybe we can use it to manage the data while it's living in particular architectures, especially in data architecture. But data governance also should extend to AI governance as well, the different data artifacts that we have. Of course, even like what we build our vectors off of, that should all be considered. And it's kind of not right now. So that's our quote unquote shit show. And of course, the more silos that you have here, the more of a disadvantage it is in terms of actually developing your AGI applications. And so, for instance, if you have, so this is one of the things that our organization works off of in terms of having a unified data catalog, is that we believe that metadata is sort of the glue between everything that can help provide lubrication in terms of the tools. And the idea is that you can get rid of these silos between the query engines, between the storage systems, between the formats, between the actual types of data themselves. Then you can speed up process, like actual development of machine learning applications and generative AI applications, so that you can have more flexible systems in the end, instead of having to go, okay, I need this piece of data for this application. I'm going to go to my data engineer. They're going to write this pipeline that maybe kind of works once or twice, and then nobody's going to look at that pipeline forever. It's going to, have some sort of anomalies over time. The actual results are going to change. We're going to have model drift, and now nobody knows what's going on, right? We need to be able to like mitigate that in some way. So if we have a unified metadata layer that actually catalogs and takes all of this metadata from the underlying system. So in this case, it might be like a Kafka messaging system. It might be a relational store, it might be your data lake. We take that metadata and then we have it interact directly with the query engines. In this case, this can be, of course, the Python ecosystem, but as well your traditional like ETL systems as well. And this is really cool because then you can have everything working off one single layer, and you can define your policies in this layer. You can define your governance in this layer, and then it's served in a unified way towards the entire organization. This is really important because even if all this stuff here is complete crap, at least you have this one layer that can make some sort of sense to the rest of your organization. So what else can metadata do? So this is from one of Gartner's analyses. They've also done a recent one on data catalogs that's really popular right now. And essentially, this is the way that we've moved towards, from static metadata to active metadata. Event triggering is also kind of mixed in this, but essentially, traditionally we've just had, consumers kind of pulling directly from data sources. And then now we've tried to move towards having these different semantic layers to make sense of operational data, and then kind of transform the different pieces of data that we might have. So then consumers can pull from a single layer. This is a traditional sort of data platform, if you will. And now that we've kind of gotten more advanced in terms of data ops, you can actually have ad hoc analyses and applications pull directly from metadata layers. And the metadata can actually provide a wrapper around your data to provide, like, let's say I want to do discoverability or search of my data. Can I actually have recommendations based off that and using the metadata and leveraging it in a way? Can I use this metadata to provide data quality checks? Can I use it to power observability? And things like that. And I think that's a really powerful way to move from. But of course, the discipline must be there for it to work. Otherwise, it just becomes a big mess. And really, kind of if we took this previous orange box and we kind of blew it out a little bit, this is really what we're meant to do with that metadata, right? It's really about enriching that metadata so that it completes the rest of our data and it actually provides some sort of semblance of visibility. And we also can actually perform data lifecycle management in automated ways. And so we can have these checks in place. We can classify the data and we can automate some of those cleaning processes and have end-to-end reporting. we can use it to power data discovery, which is really important if we're building applications. And of course, we want to connect the data together and actually remove some of those silos that we might have. And so there's a really cool thing where, as consumers, we might just have the top of this iceberg and we might just query the data and then call it at that. But there's so much in terms of governance that we require in order to make sure that our hygiene is good with the data that we're working with. So, of course, this idea as well is around end-to-end data governance. So from the source layer all the way through your medallion architecture or your ETL, we want to make sure that we can trace all of these different things as we're moving through the pipeline. Now, in terms of data cataloging, and I should at this point at least explain what a data catalog is. Data cataloging is a pretty traditional term, but essentially if we took metadata from all of our source systems and we actually stored it somewhere, and then we enriched it or provided some sort of business glossary, some sort of other information around it, we would have a data catalog, like a literal catalog of all of our data, right? Data catalogs have evolved since then to become very technical. So in a weird way, we're able to use like open table formats, relational stores, object stores, in order to like populate that metadata to then power different applications, as we've seen. And so it's really important to provide harmony in all of our sources in order for us to then serve it in a way that makes sense. And that's really the catalog that's abstracting out above your source system so that then you can just work off of the metadata itself, especially if you want federation in your system. So let's say if I was using Trino and I queried Gravitino in this case, and it was querying, say, like multiple relational stores under the hood, could that query be split so that I'm not moving data from one place to another in order to join it? Instead, I can just do that federated querying and then save myself a little bit of money, make sure that data stays where it's supposed to, and then not have to physically move it. The architecture in terms of how you might deploy this, especially if you're on a multi-cloud or hybrid cloud system, is, let's say I want to join data across like GCP or AWS, or I have a very specific data policy that I want to enforce in terms of access management. I would deploy Gravitino in both places, and then those two instances would sync. Of course, we don't really store your metadata. You have to define that metadata store. We currently use a relational store, Postgres. And then you can use that in order to do the rest of the stuff that we were just talking about, mainly around observability, your access control management, and of course, auditing. The way that this looks more under the hood in terms of our architecture is by providing a single REST interface for your different applications to pull off of. So we want this to be as easy as possible to be predictable. But under the hood, we have like a catalog of catalogs approach where, let's say you might have a relational store like MySQL that has its own catalog. We then register it into Gravitino, and then that kind of moves up into the meta lake, and then it gets managed in this layer while the metadata storage gets abstracted out. Of course, we also provide connectors for Kafka. We provide a virtual file system if you want to do unstructured data management in Python. And of course, normal distributed stores as well. And Iceberg. We also provide an Iceberg REST service. The way that we handle tabular data and non-tabular data, depending on your use case, will actually be treated differently under the hood. But generally speaking, your operations will remain the same, so it'll be pretty predictable. This is our attempt at really kind of merging the worlds of data engineering and machine learning engineering, just because we understanding and that the tools will vary quite a bit between both teams. And of course, if you want to have Lakehouse Federation, you can do that by querying over your multi-cloud systems. And the idea here is that all of this stuff is kind of abstracted out, but your analytics or data scientist teams that might be, I don't know who's using R as much anymore. I say as a former R developer, but Python and SQL, of course, those teams can be sticking to the tools that they want to in terms of querying and not have to worry about what's under the hood. So a little bit more, pretty much just kind of driving home some of the same ideas that we've had. And Of course, we have tagging now in 0.6. I'll talk a little bit more about the features in a little bit, but generally with our tag-based masking, you can have this masking in place and then train over that data and not necessarily worry about having something sneak in that you don't want to. You can also use that to enforce your geo distribution or have more row-based or column-based fine-grained control. So yeah, in my opinion, catalog RAG is not a true thing, but I do think that it should be used in conjunction with RAG to power, knowledge graph RAG or vector search RAG. Cataloging and metadata can actually be quite powerful in helping power knowledge graphs instead of just like deploying a giant knowledge graph over all of your data and hoping nothing goes wrong. That's a little bit unrealistic in my opinion. And it can be used to kind of bring some governance and guardrails into your vector searches. And I think that's really important for us to have. If you're interested, we wrote a blog post where you can kind of build a really quick data agent and get started with Apache Gravitino. It's very straightforward. If you scan the QR code, it will take you to the Medium blog post. And I will give people a chance. I still see some phones up. Awesome. And so if we were to kind of look at how Gravitino might interact with a machine learning system, so of course we use Llama Index for this. We wanted to keep it pretty lightweight, but generally speaking, instead of building all of these connectors and using it directly with Llama Index, you can actually, connect them all to Gravitino, define your access policies and your governance layers in there, and then have Llama Index actually just directly work with Gravitino. That way, the team who's meant to keep you guys out of legal trouble can do what they need to, and then your R&D teams can, actually not have to worry about the rest of it because they won't be pulling data that they don't need. And of course, if you're using some sort of agent or you want a universal agent in place, this can help provide guardrails there as well. So yeah, I think we went over some of these already, but again, if you scan this QR code, it will take you to our repo. So we're an Apache project, of course, still incubating, but generally we want you to be able to query all of your data and discover it pretty easily. We want you to have some options and simplicity in terms of how you interact with Gravitino. So we have a Java and Python client. We also have a REST interface, and we're currently building out a CLI to make it scriptable. The idea here is that if you have multiple cloud vendors and regions and you require governance, you can have that set up pretty easily. We can sit on top of different data catalogs and different data management layers. And of course, we're under an Apache license. So take it, remix it, do whatever you want with it. And in 0.6, we've released some more features. So of course, we've included our role-based access control model, which is still kind of like being fully fleshed out, but generally speaking, the idea here is to have a push-down model. So let's say I define an access control policy in Gravitino, and I want it to push down to say and translate into GCP or MySQL in multiple systems at once, even if it's different under the hood. That's kind of the idea. The Iceberg REST catalog service has been abstracted out. That was really a big request from us. We also support tagging. You can now directly query us using Flink. We also support Paimon, and we've added S3 support as well.
Who would call Paimon? I thought it was Paimon.
I don't want to get in an argument right now. But I've always called it Paimon. Okay, Paimon? Paimon. See, neither of us are right. Neither of us are right. Yeah, it's Apache P. So this is our community that's currently using us and contributing to us. Happy to say that Zilliz is on there as well. And on to the Star Trek portion of this that I know you all have been waiting for. I have 2 prizes to give away. So first person to answer this gets the prize. Okay. Worf is correct. You can come up here and grab your prize. Okay, I have 3 questions, so hopefully we have enough. One is XL and one is double XL. I'm sorry. I travel with a carry-on. I couldn't bring all the sizes. Okay. So yeah, O'Brien would have also been a legitimate answer. So next question. What rank is data from the next gen? Almost. Lieutenant what? Oh, I want to split between you two. Can one of you say it, the whole thing quickly? There you go. Okay. And I think we're out of prizes, but we can give you a pin and maybe some extra candy. I just want to see who gets this out of bragging rights. So I was a little bit concerned that maybe you guys weren't nerdy enough. I was clearly wrong. So of course, who's the captain of the Voyager? that question was a mistake. Nobody? Who said Janeway? Who said Janeway? Yeah, it's Janeway. That was, oh my gosh.
We have a pin.
Now we have do we have a pin left over there? That disappointed. I want all of you to go home and watch Voyager tonight. That was. Oh my gosh. Okay. Well, thank you all for being here and for listening to this talk, and enjoy Star Trek. There you go.
That was awesome, as always, and cool giveaways. Now, did you get the link? Do you want to use your laptop? That's probably easier. Hopefully you also have some Star Trek stuff. Do you want the clicker? Oh, got his own stuff.
How do I connect?
It is Zoom, which I sent you.
Okay.
We could also plug in, but it may be tricky.
Hey, can you hear me okay? Yeah. Awesome. Thank you for coming. I'm
Turn off your laptop.
perfect. Yeah.
You know what you
Okay. Sure. Yeah. I'm Naren, one of the co-founders of Unstructured. So we are an open source platform that extracts structured data from unstructured documents. And we do it at scale using large language models. Right. Okay. So I'll quickly walk you through the agenda. So basically, I'll talk about the limitations with the current systems in this problem, right? Extracting data from unstructured documents, and how, like, for example, like a lot of businesses deal with this problem. Like, let's say you're applying for a loan, or let's say you're dealing with insurance where you're submitting a claim. Then you upload a bunch of documents. It can be, let's say, a hospital bill, or for a pay slip, or it can be any like a bank statement. And what happens is that now these documents need to be processed. And when you extract information from this, like these documents come in different forms and shapes. Like, for example, if 200 people are applying for a loan, and they are processing, they're submitting their bank statements. And if they have banks in different banks, accounts in different banks, what happens is that like you need to like upload, like extract information from these documents. And it's not easy. And the current systems, it's like very painful, because you need to manually annotate the documents and then do the extraction. And now with LLMs, right? This has completely, now this, as we speak, this is getting disrupted. And you can extract information from these documents without any training, just by prompts. And of course, LLMs also have their own limitations. And we'll talk about like one important or very common one is like hallucination. How do we deal with it? And of course, I'll give a brief introduction on the platform itself, Unstruct. And main like the area I want to focus today is like extracting information from long documents. Like we deal with documents which could run into like several hundreds of pages, and we need to like, that is where a vector database is super important. And today I'll show you how you can use Zilliz, for example, to actually do the extraction from these long documents. And we'll see this without vector database and with vector database, so that you know like exactly like how I mean, from a cost standpoint and from an extraction quality standpoint, how this kind of impacts. So I'm Naren. I'm one of the co-founders. And one thing I'd like to highlight here is that we process close to 5 million pages per month on the platform. So we know like we have dealt with like a lot of different types of documents, and these documents are like very, very like different variety and across industries. And I'll give you like more examples as we go. So when you look at the PDFs, right? So state of the art today, you deal with like tables, like it's very common, like tables are spread across multiple pages. And then PDF forms, right? Forms will have checkboxes and radio buttons. How do you ingest them? And then scan documents, like there are like decent scans, which are like flatbed scans, which are like easy to process because the quality of document is good. But we are in real world, we deal with like now everybody takes their smartphone out and then they take an image of a, like say a form. And even worse is forms which are like hand filled. And these forms, like even checkboxes, hand ticked and all that. And how do you process that? And how do you process that accurately? So that's the problem we deal with. And of course, in real world, right, the main pain is today state of art, like the previous generation stuff, where you need to like do annotation manually and then do the extraction, and it's not easy, and it's very, very time consuming. And also like this kind of slows down the entire business. Like, so how do you do this using like LLMs? And one thing like okay, like so there are co-pilots, right? So how we are different from co-pilots. So you could just upload these documents to say ChatGPT and do structured extraction. But ChatGPT, when you ask for structured data, like every time it might give a different schema, and you need to define the schema. And even then it is for human consumption, right? So the human sees it on the screen, and then they need to like, they can of course copy paste it into, let's say, a system of record. It can be Salesforce, or it can be a database or data warehouse. But they tend to make mistakes. And also humans like are very tolerant, right? If you give us any date, right? So it can be 20th January 2020 or January 7, 2020, or let's say 0701 2020, like humans immediately get it. But if you want to, let's say, have a dashboard downstream, and you want to have if the dates, for example, are coming in different formats in a document, then you need to standardize before you can actually do the extraction. And then once the extraction is done, you need to standardize before you can send it downstream for powering these dashboards. So we believe this is incomplete automation. So what we focus on is machine-to-machine automation, where in goes this unstructured document, out comes structured JSON, and we write it to the system of record. It can be, let's say, a Snowflake or BigQuery or Postgres or any database or data warehouse. And of course, the document data extraction, right? This has been a problem that has been around for a long time. And OCR has been there for a while. And OCR, like it doesn't have any intelligence, but it does extraction. And then came machine learning based systems, which uses computer vision. There is like very little tolerance for change in the shape of the document. However, now today, this is getting disrupted with LLM based systems, where you could extract data. I mean, you just need the input, the context, right? The context, you need to give it to the LLM, and LLM does a very good job at it. Like say, for example, you don't need to rely on positions anymore. Say you're wanting to extract policy holder name from insurance policy. It can be on page 1 on third paragraph in one policy, and it can be on, say, page 3 on second paragraph in another policy. It doesn't matter. So it does extract pretty well. Now, Unstruct is an open source platform. And just like, I mean, on a very high level, we give you the flexibility to choose your LLM stack. So we connect to, we have connectors to all the LLM providers out there, vector databases, embeddings, and also text extractors. So you can pick and choose whichever you want for your particular use case. So in Unstruct, think of it like there are like 2 phases. The first phase is the prompt engineering, right? So how do you define the schema for extraction? So you can like upload a sample set of documents and then write the prompts. And then once you're comfortable with the prompts and make sure, and you're fine that the extraction works, you could then deploy it as a API or a ETL pipeline. So for example, let's say you have like say a bank statements, like I was mentioning earlier, you just like write the prompts for these bank statements, and then you deploy it as an API so that you could send any bank statement to this API and get structured JSON back. And of course, I mentioned about hallucination and all the problems that comes when you are doing this in production, right? So LLM challenge is one of the features which is very critical which we see being used in production, where you can set up a second large language model. The first model does the extraction. Second model challenges the extraction, and both the models should come to a consensus, without which the value is set as null. So we believe in philosophy as a null value is always better than a wrong value. And this kind of like increases accuracy to like 98, 99%. And of course, there are also some features like single pass extraction and summarized extraction for cost savings, because how do you optimize the tokens and so that you can also like save on latency. And this is super important, particularly if you are dealing with large volumes of documents for doing extraction. Yeah. And I'll quickly now walk you through the platform and also show you how the extraction works. And then mainly in this example where we are using Milvus for doing the extraction. And we'll look at the different extractions for from the 10Q document, right? 10Q is a document that's filed by any public company to SEC. It's a quarterly filing. And if you want to extract from that, then we'll do it without vector database. And then we'll do it with vector database. And we'll talk about what are the different strategies you could use for extraction, even using vector database, how you could do the extraction for particularly long documents. So we'll first look at the without vector database, right? So this is a platform. And here you can upload the document here. And then I have set up 2 large language models. One is GPT-4o, and then I have Claude Sonnet 3.5, so that you can see side by side how is the extraction. And mainly what you see here is the tokens and the cost. So you can see GPT-4o for this, we are for this extraction, right? So here, this is a JSON key, registrant name, and then we have the prompt here. And then here, we are not using a vector database. So this 28-page document, we are sending fully to the large language model. So you can see the tokens are pretty high. Like, I mean, it's like close to 60,000 tokens. And Claude, it's even higher. And the cost for extraction is also like quite on the higher side. For just extracting this one field, it's like 15 cents, which is a lot. So how do we now reduce this and do a better job at it? Like, so we'll talk about that. And one thing I like to highlight in this is we have a text extraction service called LLM Whisperer. So what it does is that it extracts information in a way the large language models can understand. So we do something called layout preservation. So with layout preservation, as you can see, when we send this to the LLM understands the document really, really well. And even the tables, right? So the layout is preserved. And when you send this, the extraction quality is very high. And so now here we have multiple prompts. So you can see what is the file number, and then we have jurisdiction state, and then IRS employer ID and all this. Like, so we write all these prompts, and you can see this is the combined output. So basically in goes this document, and then this is the structured JSON, like, so registrant name, file number, jurisdiction, address. So we have all the prompts here. And this is the combined extraction for this particular document. And I mentioned about challenge, right? So this is the LLM challenge. Like for example, in this example, so we have GPT-4o for the extraction and Gemini Pro for challenge. And this is a challenge log where we are like having a score for each of these, and we are emulating a score, so we know that it's being extracted accurately. So what I'm going to do now is that I'm going to deploy this as an API, and then we have an API for this, like without vector database, right? So I have the API endpoint here. So you can download Postman collection, or you can also manage keys, and then we also give you like say code snippets to do the extraction. So let's look at the cost, right? Cost for this. So I'm going to go to Postman now, and then let me. So I have this without vector database, right? So I have this endpoint now configured. I'm going to just send this file, the 10Q report to this is another 10Q report. This is for Q2, and then expect structured JSON back. So you can see how like beautifully structured JSON has come, and then all the now I have metadata on, so it means it is returning the entire chunk and all that. And I'll go to the very bottom where I have the structured output. So you can see this is the output of the model, and then you can see the structured JSON for this particular document, right? So main thing I want to highlight here is the cost. So you can see this document, we have spent like close to like north of 250,000 tokens, and the cost for extraction is more $1.4, which is actually a lot for just this one document extraction. Now, thanks to vector database, so now we can bring this down and we can do a very good job at it. So I'm gonna go back to the platform, and then I will show you another project where I have a vector database setup. So yeah. So here I have 10Q parser with simple retrieval. So here I have a vector database configured. So you can see here I have so GPT-4o as the model, and then Azure OpenAI embedding, and then I'm using Milvus on Zilliz Cloud, and then I'm using LLM Whisperer as the text extractor. And you can see here, I'm even like set up like the chunk size, right? The chunk size and overlap is all set up here. And then the retrieval strategy here is simple retrieval. So I will talk about simple and sub-question retrieval and then how that is different. But here for simple retrieval, right? So let's look at like how this is like working out for this particular use case. Now, you can see the tokens, right? Previously, the tokens was very high for each extraction. Now the tokens has come down drastically because we are chunking the document. And when we are chunking, only relevant chunks are sent to the LLM, and then the extraction is done. So that way, the cost is also like very much lower compared to how it was done earlier without chunking. And I'll again now go to Postman, and then go to this other one with vector database and with simple retrieval, and then run the extraction again. So you'll see now again I've turned on metadata, so you can see it has like all the it returns all the chunks as part of the output. But mainly I want to show the cost, right? Now earlier, the cost, right? It was more than $1.43. Now you can see with vector database with Milvus turned on, the cost has come down to just 17 cents with simple retrieval. So this way, even if you're extracting from long documents, then probably like this is a better idea, like this is a better way to go about, right? And let's go back to the presentation where I'll talk about this a little bit more on the how this works overall, right? So now this is a typical RAG, right? So you are you might be like pretty familiar with this. So in this, like of course there is a user query, which is the prompt, and then this is sent to the embedding model, and then you use a vector database like say Milvus, and then the Milvus returns the actual chunks as per your query, and then the user query and the chunks are sent to the LLM, and then the extraction happens, right? So this is a simple retrieval. Now, simple retrieval is good for most cases, or like where the complexity of the prompt is not very high, where you are extracting something very. If it's a very simple, then it works pretty well. However, if the complexity of the prompts gets more and more, if you are extracting a lot of things in let's say a single prompt, or let's say the information is present across multiple chunks and all that, now it gets even more complex, and then like so you might need sub-question retrieval as another way to do the extraction. So the simple extraction, right, the simple retrieval, where like if this information is available, as like I mentioned in the return prompts, then it's super easy. It's also like cheaper compared to sub-question strategy. However, it will work only if the prompts are simple. So for sub-question, what happens is that the LLM is used for retrieval, but the prompt is split into multiple sub-questions. So each question is now sent to the LLM, and then the vector database, and then the multiple chunks are now returned, and then the chunks are deduplicated, and then the extraction is done from the specific the chunks which are actually finally returned. So this way, your prompt is broken down into multiple sub-questions. Thereby, the accuracy of extraction can go up a lot. And this sub-question retrieval is also available as part of same in Milvus, where in Unstruct, it's very simple for you to just go and then just change the mode of retrieval as sub-question retrieval. I'll show that here. So if you go to with sub-question retrieval, so here everything is like very similar, but only thing I'm doing here is I'm again using GPT-4o for the LLM, and then Zilliz Cloud for vector database, and then LLM Whisperer for text extraction. However, here I'm choosing the retrieval strategy as sub-question. So what happens is that now we are able to extract even like the complex stuff, right? So here I'll show an example of a prompt. The ones at the top are very simple, but if you look at the income details, right, here this prompt is pretty complex. Like, so you have like from the statements of operations or the income statements, respond with the following JSON object, and you're asking for very specific things, and there are also more instructions at the bottom. So how does that work, right? So here we have this extraction done, and then I will show you the cost of this. Right, I again set this up in in Postman, and then yeah, this is with sub-question. So here you can see the extraction. The cost in dollars is little more than simple retrieval. It was like 17 cents if you recall. Here it is like close to like 23 cents, but the quality of extraction is much higher. But here, this example right here, the document, the 10Q is pretty straightforward. Like, it's not a very complex document. So the extraction is also not very very complex. However, let's make this complex, right? So where can a simple retrieval strategy fail, right? The simple retrieval strategy, because if you are doing this in production, then you are compressing the prompts and you are trying to extract most of it in one shot. So here, in which case I have an example of a prompt. Here you can see it's only a single prompt, and it's pretty complex. So it has a lot of information, and it has like a lot of and also the instructions and all that, right? Now, when you use this, like you can see the tokens used is much lesser, and the extraction cost is also not is lesser. However, for simple retrieval, you get some nulls because because of the complex nature of the prompt. The LLM is not the vector database is not able to return the right chunks with all the information. So what happens is that it is returning null values. So how do you fix this, right? So this is where sub-question retrieval helps a lot. So I'll show you the other example, the same example where the sub-question is turned on. So the compact, compacting the prompts, but here, yeah. So it's the same prompt, but here the retrieval strategy is sub-question. So if that is the case, then you can see that you're getting the answers right from the LLM, because the vector database is returning the right chunks, and multiple questions are generated, and then the answers are retrieved. So to summarize, so if you are like using a full document, right? If you are like extracting from a full document, particularly if it is like a smaller document, right? Like say, for example, invoice or a bill or a form with like, which like has like maybe a couple of pages, then you can extract it with very high accuracy, and you don't even need a vector database. However, for many use cases, you will need a vector database. And if it is particularly a longer document, then you can use a simple retrieval. However, the cost is very low. However, the accuracy of extraction depends on the complexity of the prompt. If the prompt is super complex, then it is not going to like give you more accurate results. So it's better to use sub-question for most part. It's slightly higher than simple retrieval, the cost of extraction, but accuracy is also pretty high. And this way, the complex prompts can be broken down and then sent to the vector database so that the extraction is done with high accuracy. Yeah, and you can find me. These are the relevant links. Like you can check us out, and then we have an open source offering, and even LLM Whisperer is the text extraction service that's also available, and you can check it out. Thank you. Any questions? Yeah.
It's a PDF extraction, right?
Yeah.
So sometimes when people type it on Word and convert it into PDF, there is some words that convert into image, which are not exactly extracted. So I wanted to know if that would be extracted as well with the help of GPT?
Not with the help of GPT, but that's why we use the LLM Whisperer, the text extraction service. So it can convert, like say, even images or handwritten text or text within images, and then native PDFs, scan PDFs. It can be anything. So it takes care of that and converts it into plain text, which is what is sent to the LLMs for extraction. Yeah. Yeah.
Your detailed prompts, are you auto-generating those detailed prompts, or are you actually going in and creating those?
No, we're going in and creating those. That's deliberate process, because how do you know that the schema, right? If you want to define that and if you want to extract, and then how do you know the prompt is working across a sample set of documents? So for example, let's say you have like insurance policy and you have like 20 of them. One prompt may not work across all the 20. So this is the prompt studio is for prompt engineering. Think of it like a IDE, but for prompt engineering. Engineering the prompt. Yeah. Exactly. Yeah.
So essentially, the customers are given access to the studio. Is that how it is?
Yeah, it's a whole platform is open source. Like the whatever studio you saw, just like you can go to GitHub and then download and then use the platform. Yes.
And what is the next? Like, are you also thinking about like computation as well? Like there's a structured like a document, but then you're thinking about can you do computation on it also, or more or less you are solving for extraction?
No, we are solving for extraction because we have seen customers, right, when they do computation, right, that's an easy problem. Like once it's converted into structured data, because LLMs tend to not, we cannot trust the LLMs for doing that. So what we do is that think of it as a breakdown into two steps. First step, you just do the extraction accurately. And then like we have customers where the loan decisioning is a real example, where they want to like calculate, let's say, the debt ratio or like the withdrawals and then deposits ratio and all that, right? So we ask them to just do the extraction and then do it as a next step post-processing. It's very easy, right? It's like dealing with any structured data, and then it's you can do programmatically. Yeah. Yes.
First, thank you for the nice presentation. And my question is about the cost. It's like it's not really about like your product specific, but it's more like cost. It's like when we think it's like if now I need to process automatically PDF, but I can use the OCR, like what they're saying is like some machine learning and I can automate it. I have the cost of like, yes, I need to have a machine learning engineer, someone like maintaining it, but then it's just like a WS cost of cloud cost.
Mhm. Mhm.
Why do you think is like that LLM will be cheap enough to be because like if I need to process, I don't know, 10,000 documents a day, this would be like a good amount of money every day.
Mhm.
The usual calculation is like maybe some company can afford it, but when do you think it will be
Yeah.
like, possible to do it like in a efficient?
Yeah, that's a great question. See, at the like 6 months ago when we showed demos, we showed with GPT 3.5, then we showed with GPT 4, now with 4.0. Every time the cost is like the previous demo when I did, the cost here, it was $1.4 for extraction, right? That itself, we are saying it's high. But previous demo with GPT 4, it was double that. It was more than $3. So as we speak, the cost is coming down for the models, but the pain is very real, right? We are seeing documents like wherever the businesses are interfacing with the external world, where they don't have control over what documents are coming in, then this is a huge problem, because every time otherwise they need to go back to the drawing board, do annotation manually, and then do the training and all that before they can even start doing the extraction. And it's like undifferentiated work, right? So particularly like the good examples are the loan decisioning, or in let's say the mortgage decisioning, loan decisioning, and insurance claims is like two top examples where the incoming document, you do not know how it's going to look like. So but from using LLMs, you just give the context, and also think of like the label data and all that, right? Like what about, let's say we have seen examples where in 4 different policies, each one it's referred as name, customer name, policyholder name, and then let's say insured name, like all this. Like now the LLM is smart enough. You just need to ask what is the name of the customer. That's it. It gives you the extraction across all this, right? So it's like super intelligent. See, another example I'll give you, like also without training, you can use LLM's knowledge for doing some extraction. For example, we're dealing with a customer who wanted to extract from resumes, and they had like a bunch of things they extracted. All of a sudden they wanted to also add one more column where they wanted to extract the country name of the candidate, right? The country name is not explicitly mentioned in the resume at all. The country name is not mentioned in the document at all, like in the resume. It just says, let's say, Chennai, India. And then, or just says Chennai. And then the LLM understands and then puts India automatically, right? So it knows this place is in this one. These kind of, a lot of use cases, you can go above and beyond what machine learning can do. So yeah, these kind of things. But of course, this is only for the knowledge coming from the LLMs, right? Not it's not safe to ask anything computational. If it is from the knowledge of the LLMs, then it works very well. Yeah.
I have a follow-up question.
Yeah.
When the thought of an LLM being expensive was brought up, I just wanted to ask, on this platform, can I use open source models like Gemma and Llama? So
Yeah. Absolutely.
Because they've gotten a lot better.
I mean, if I can use Gemma or Llama, so do I need to train them on my machine? Do I need to have all that processing power, or will it be provided by Unstructured for free to some extent? So what will be the limitations?
Yeah, so we connect, this is a very common question we asked, particularly not from a cost angle, more from a privacy data security angle. And we integrate with all the popular ones out there. Like you see, these are all the integrations available for you to, once you take the open source repo and use it. We have OLAMA integration. So you can connect to any model using OLAMA, the locally self-hosted model or a trained model. And we also have AWS Bedrock, right? We got this integration because, again, customers were not comfortable to send the data outside their AWS environment. So they could use like all the AWS services. This is one of the other AWS service. And we have like customers who use like contract extraction, where they use AWS like Claude Sonnet 3.5 for extraction, and Llama 3.1 for challenge. And so, yeah.
Thank you.
Yeah. Yep.
I'm actually have a question about the accuracy of the user AI.
because you use the example 10Q. So in the 10Q, they could have the same information. They have multiple times appear in the same document. For example, the address, for example, the revenue on the consolidated statement or then in the parent of the sub-company. So for LLM, it's very difficult to actually extract the information based on context. So even for multiple models, you get the same answer, but it's still not. It's not correct. How did you actually correct that?
Yeah, so it's usually what we have seen is that it's a prompt engineering problem where that's why we try to have like multiple samples in the upload and then write the prompts and then do the extraction. It depends on the use case really. So
different companies, they have the 10Q rates on the different section. So you have the same from us, but it doesn't work for a lot of companies. 10Q.
I'm not.
Even the same company, the 10Q this year, next year.
Formatting could be different where they put
because
stuff.
it's document, it's a natural language, so people write it randomly. So
yeah,
we do this. Previously, I worked on Bloomberg. It's actually I did this part. Extract the data from the statements. So
yeah,
we actually use it.
Usually it doesn't matter because what we have seen is that like you do it with a good sample set. Like for example, we do SAS contract extraction. I can show you an example of this SAS contract, right? So this is the, just give me a second. I'll show you an example of like very, very varied documents, but it will work well if you like properly use it with like, for example, see, this is a real example of a contract and it has like, no.
This is a document.
Those documents can be 100 pages long.
Yeah, 10Q. You use the 10Q.
Oh, 10Q. Okay.
Images and all kinds of weird stuff.
Yeah. So 10Q, it's 10Q is easy, right? Because it is like, it's a clean document. It's a clean document.
No, it's very complex.
Not if you're doing all of them in the world. Like,
yeah, you put the company, you put from this year to next year, they change. People change, they different format.
No, see, I don't know. Like, I mean, from a 10Q standpoint, like, I'm not like a 10Q expert. I'm not a 10Q expert, but we have seen like use cases where like really like completely like you can see these documents, right? These are like fit into one single schema. You see like all of them look very different and they want to extract from this SAS contracts. Yeah, and it works. So I think, and one other thing I would like to highlight is also the LLM Whisperer, right? Maybe, I don't know if you have used that. With LLM Whisperer, we maintain the layout of the document. That makes a huge difference in accuracy. So you might want to try that also. Like say here, right? When I showed you the 10K example, right? The LLM Whisperer, even for forms, handwritten stuff and all that, I'm telling 10Q is easy because it's good quality without any, like it's not scanned, right? So you can see this one, right? This document, this is converted into this before sending it to the LLM. When you do this, and then if you are able to do the extraction, I'm sure the quality you will see is much, much better.
But you are extracted the specific number from here.
Yeah.
Because I did this for 50 years.
Yeah, but LLMs have been around only for like last few, yeah.
For example, if you deal with the 10Q for different markets, for example, Hong Kong market, they all have different, the table is unstructured, there are no borderlines. Very difficult to actually reconstruct the table. I didn't use the LLM Whisper, but I'm sure it's very difficult for you. LLM Whisper to unstruct the Hong Kong market for 10Q. With the other report. So.
Yeah, you might want to try it out. I mean, yeah. So you should check it out. Yeah.
Look at Copilot. Copilot is doing some interesting variations of something if it's a really weird format. Because it grabs them out as images.
For 10 years.
Yeah. So
Anyone who's asked a question, come up and get some merch.
Yeah.
We have different sizes in the front here. First come, first serve. It goes from smaller, they are Chinese sizes.
you give me some.
Three sizes smaller. So we like, I can't fit in a 4XL. I wear 2XL Chinese sizes, skin tight on it.
Too, but they're meant to
But
be
we
very-
tell you it, because we found that out. Because 4XL is not a big shirt. I guess we're good.
Any other questions? Yeah.
So in the prompt engineering point,
Yeah.
is there any way for you to compare pricing in between different models? or
The
anything
socks
like
are
that?
normal
Or
sizes.
decide
Why not?
between, let's say,
I have two
different
pairs
LLM
of socks.
providers?
They're
Yeah. So that's what we do here, right? So here you have the prompt and then side by side. So you can see this is the cost 15 cents and this is like 19 cents. So side by side. Yeah.
More than just two?
T-shirts and
Or
stickers.
right now, the
No, we allow you to see up to 3. Yeah, at a time. I can show you another example where we have 3 set up. So this is a credit card statement extraction. So I have GPT-4, Gemini Pro, and Claude Instant. So we allow you to set up to 3, and then you can see side by side. Like it's easier to see this way. So you can see the extraction. Yeah.
And with the open models, it'd be a lot cheaper.
Yeah, open model will be a lot cheaper, but state of the art, we are seeing it's still, yeah,
I mean,
depends
Llama
on.
3.2 and Lava are pretty good.
That's pretty good. Yeah.
Every day there's a new model.
Yep. Thank you.
Thanks all the speakers for coming. Grab any food that's left, grab drinks, grab stickers. Speakers are still here if you want to ask them questions. You don't want to say it out loud because you think it's silly. There's no silly question, just bad answers.